Imagine a catastrophic IT outage triggered not by a server failure or a massive electrical fire, but by the system designed to protect the building. A single faulty sensor reading releases a cloud of suppression gas that floods the data hall. In mission-critical environments, a false suppression discharge is financially equivalent to an undetected fire. Both result in millions of dollars in downtime, hardware damage, and total operational failure. To defend against both threats, the fire alarm functions as a high-stakes computational engine, actively sensing conditions and executing decisions based on pre-calculated logic, rather than simply sounding a bell for code compliance. This hardware ecosystem is coordinated by the fire alarm control panel. It acts as the core authority, processing inputs from initiating devices on the left to trigger outputs on the right. Remote enunciators provide awareness, but the FACP alone maintains ultimate command authority. Looking at this classification matrix, we see how the system prevents panic by separating incoming data. Red alarm signals require immediate emergency response, while orange supervisory signals indicate off-normal conditions in subsystems, like a closed valve, that require maintenance but not an evacuation. Data center reliability rests on operators trusting these distinct signals. If the system creates ambiguity between a dirty sensor and a fire, humans often make errors in judgment that lead to unnecessary shutdowns. Effective fire protection avoids the trap of a generic blanket strategy applied evenly across a floor plan. This protected space application map shows how the threat profile changes across functions. In central data halls, high-velocity airflow is the primary obstacle. But in battery and ESS rooms, the threat shifts to gas emissions and thermal runaway, requiring coordination with shutdown strategies. A defensible architecture maps detection technology directly to the physics, fuels, and airflow of each isolated zone. Traditional ceiling-mounted detectors often fail in data halls because massive HVAC forced air currents blow incipient smoke straight past the sensors. Effective detection follows the physical movement of the air. This diagram shows smoke forced into return air plenums and underfloor supply. To catch that smoke, aspirating sampling points at positions 1 and 4 are positioned exactly within these high-velocity paths. This detector selection matrix compares technical applications across the facility. High airflow data halls require aspirating, or VESDA technology, because it thrives in these high-velocity environments where other sensors remain blind. If the system isn't hunting smoke along HVAC return paths, operators won't know there is a problem until thermal damage is already irreversible. Digital logic is only as reliable as the physical copper and batteries supporting it during an outage. This workflow shows the mathematical rigor to size standby power. It calculates a mandatory 24-hour standby term, and in Step 3 accounts for a 15-minute high-load voice evacuation state, plus a 25% safety margin. Voltage drop is a constant threat. Step 4 proves a 24-volt supply can drop to 20.6 volts over a 50-meter loop. Engineers must reserve headroom against the 16-volt minimum to survive temperature degradation and source drops over time. Reliability requires extreme precision in the analog electrical calculations that keep the sensors and notification devices alive. There is a common desire in facilities management to merge every building system into a single dashboard for convenience. Over-integration is the highest risk to the data center. A defensible design uses the FACP to separate red life safety command interfaces from blue monitor-only interfaces. External IT systems must never be granted undocumented control authority over listed life safety logic. These rules of engagement allow external systems to observe data from the network while preserving life safety primacy. They can pull information, but they are never allowed to execute commands. We see this separation of duties applied to the most critical output, gas suppression release. Gas actuation must be managed strictly by a dedicated releasing control unit, ensuring the initial alarm is separated from verified countdown and discharge states. System resilience comes from isolating the authority of life safety components from the vulnerabilities of the broader IT network. We bind the hardware together using deterministic cause and effect logic, where every scenario is pre-calculated. Terms like as required are forbidden because every matrix row must represent a specific, testable outcome. This logic governs the phased data hall sequence. At phase 3, a single smoke alarm isn't enough. Explicit verified criteria must be met before starting the pre-discharge timer. Furthermore, the emergency red philosophy dictates physical safety must be confirmed before any system reset. This choreographed sequence prevents human panic from causing a premature and costly agent discharge. An architecture is only defensible if it can be physically proven through rigorous field testing. There is a critical line between component acceptance tests and integrated system testing, or IST. A component test checking individual wires does not replace an IST. The IST verifies end-to-end interactions across HVAC, door releases, and emergency power. Unmanaged software updates represent an invisible risk over time. Any change to firmware or the system database mandates a repeat of the affected IST cases before the panel returns to service. Validation requires a continuous governance regime that survives for the life of the facility, long after the initial handover is complete. Human failure remains a significant threat. When a nuisance alarm sounds, the immediate instinct is often to blindly hit reset to clear the board. This troubleshooting model replaces panic with process. Operators must capture synchronized event logs and voltage states before resetting. Software settings should never be altered to fix a physical wiring or environmental fault. Building a defensible system requires approving the design basis before selecting logic, mapping detection to airflow, enforcing interface boundaries, and writing deterministic sequences. The fire alarm system coordinates your entire response strategy. It is the final line of defense against operational chaos in the mission-critical environment.